Continuity equation in case of my three-dimensional flow. Okay. So first, we are considering an element that have the length of dx, dy, and dz in x, y, and z direction. So first I draw a figure. This is my face A, B, C, D, E, F, G, H. Okay. So in case of x direction, we are assuming the velocity is u. In case of y direction, we are assuming the velocity is v. And in case of z direction, we are assuming the velocity is my w. The velocity component is my w. Okay. And this is the element length, that is my dx, dy, and my dz. Okay. So we are considering the so we are considering this fluid element which having the dimension, that is my dx in x direction, dy in y, and dz. Okay. And the velocity, that is my u, v, and w in case of my x, y, and z direction respectively. Okay. So first we are calculating the mass which is entering in this phase and leaving in this phase in x direction. Okay. So what is the mass which is entering? Mass of fluid entering the phase A, B, C, D per second. Okay. So what is the mass which is entering in case of my in this phase? That is my rho AV. Rho area is area. This is my area. So what is the area? That is my dy into dz. Okay. So I directly write it down. That is my dy into dz. Okay. And my velocity. So what is the velocity in x direction? So the velocity in x direction, that is my u. So this is the mass of fluid which is entering in case of my phase A, B, C, D. Okay. Next, we are calculating the mass of fluid leaving the phase, that is my phase is my EFGH. EFGH per second. Okay. So according to the Taylor's expansion series, we can write rho u dy by dz plus del by del x rho u dy dz multiply by dx. So this is the expression is written by the help of the Taylor expansion series. So we are neglecting the higher order term. So this is my equation. And if we are calculating the net gain of the mass in x direction, so we can write mass through A, B, C, D minus mass leaving the phase EF, GH. If I am calculating the net gain in mass in this element, so how we calculate? Suppose my 5 unit will be entered in this phase through this phase and 4 unit will left this element. Okay. So what is the net gain in the mass? We just 5 minus 4. So this is how we can write this equation. Okay. So after putting the value, we directly write down the equation, that is my minus del by del x rho u dx dy and dz. Okay. Similarly, we can write in case of my y direction minus del by del y rho v dx dy and dz. In z direction minus del by del z rho w dx dy and dz. Okay. So total gain in the mass we just add net gain in mass in x direction, net gain in mass in y direction, and net gain in mass in z direction. So we can write minus del by del x rho u plus del by del y rho v plus del by del z is rho w in bracket, that is my dx dy and dz. Okay. So as you know that according to the conservation of mass, we cannot create the mass and we cannot destroy the mass. So the net increase of the mass per unit time in case of my fluid element is must be equal to the rate of increase of mass in the fluid element. Okay. So the rate of increase of mass with respect to time is my del by del t rho dx dy and dz, or we can write del rho by del t dx dy and dz. So by equating the equation 1 and 2, we get the final, that is my del rho by del t plus del by del x rho u plus del y rho v plus del z rho w is equal to 0. Okay. So now we are applying the assumptions for in case of my steady flow, this term will be 0. In case of my incompressible flow, the rho is constant. So we can write steady and incompressible flow. My equation will be del u by del x plus del v by del y plus del w by del z is equal to 0. Okay. In case of my 2D flow, in case of my incompressible, steady, and two-dimensional flow, my equation will be del u by del x plus del v by del y is equal to 0. Okay.